So Galileo, right? We know Galileo from many things, but one of the things he did was showing that heavier objects do not fall faster than lighter objects. And the story goes that he actually was dropping like cannonballs of different weights from a high distance, right? Maybe he was standing on the Tower of Pisa. That makes the story extra nice, right? The Leaning Tower of Pisa. But what he really did was he was rolling objects, down inclined planes, and he noticed, the weight doesn't matter, right? The heavier ones really don't go any faster than lighter ones. But what is less known is that Galileo, in fact, had a purely conceptual, if you want, a purely analytical, almost a purely logical proof for this. Which seems weird. How can you use pure logic to establish a result in physics, right? It's not 100% pure logic, right? But it's a large part of it, right? Because here's how it goes. So hang on. First of all, I need a heavy object. Here we go. Oh, and of course it's in yellow. Yes, great. Color. All right, here we go. Oh, I'll still make them kind of like cannonball-like. Here we go. So suppose Galileo really had two cannonballs of different weight, and I'll just have the size represent the weight, right? So the larger one is indeed the heavier one, right? And the intuition, of course, of many people is, the heavier one will go fast, right? That's our intuition, and it's kind of surprising that it wouldn't be, right? But let's see what would happen if indeed the larger one would drop faster than the lighter one, right? So I'm going to give it a bunch of speed stripes here as it's falling down, right? Kind of cartoon version, right? So the large one gets one stripe, and the lighter one gets only one stripe. So that's the assumption, right? We're going to assume that the heavier one actually does fall faster than the lighter one, right? So this is our assumption. Okay, now, Galileo said, okay, that's all well and good, right? But suppose now that I put a rope in between. Imagine this is a rope that I attach to both of those cannonballs somehow, right? What's going to happen? Well, at first the rope is, kind of slack, right? You can imagine it's kind of slack, but the heavier one keeps falling faster than the lighter one, right? And so after a while, it should look like this, right? And now the rope is taut, right? And at that point, what will happen? Right? Well, see, and here's where some of the observations, I guess, of reality come in, right? But we say, look, if say we hold hands, right? But I'm a faster runner than you are, right? Well, then I can possibly, by pulling on you, right? I can presumably I can make you run faster than you normally would. Only at the same time, though, you kind of become a drag on me, right? I can't run as fast as I normally can. So how can we symbolize this? Well, how many speed stripes should we get? How about two, right? Sort of in between, right? This whole thing now, this whole construction, right? This one thing now moves with the speed, between the heavier and the lighter cannonball, right? But wait a minute, this one thing now has a mass of what? Well, more than the heavier cannonball, right? So by our assumption that heavier objects fall faster than lighter objects, it shouldn't have two speed stripes. It should have how many speeds? It should have 4 speed stripes, right? It should have more than 3, right? So on the one hand, we say, it should go less fast than the heavier of these two cannonballs. At the same time, this thing as a whole should fall faster than the heavier cannonball, right? Well, that's a contradiction. It can't both go faster as well as less fast. Right? So I think that's a really nice argument, right? And there's very few observations that you would actually need, right? Basically to get this idea of a pull and a drag, right? That's something, and we have enough experience with reality to indeed see this, right? That things get pulled, that things get dragged. So I also think I think it's such a nice argument, and it's so much based on logic, right? That I think it's actually pretty profound, actually, right? That it's almost as if something like an argument like this should really be almost at the foundations of physics, right? Because see, of course, you can use Newton's laws, right? talk about the force, right? And hence, force equals mass times acceleration, right? And acceleration is, basically what we talk about here is speed, right? But, right? So you can talk about it in that, and then of course, what will the acceleration be? Well, what's the force here? The force is gravitational force that we're talking about here, right? Well, what's the gravitational force? We have a formula for that, right? What is it? It's the masses multiplied divided by the distance, something like that. I don't even know, right? Times of course some gravitational constants, right? Anyway, if you now figure out, okay, so what is the acceleration that an object will move with, right? Well, that would be, what is it, the force divided by the mass. Ah, there you go. And now the mass drops out, right? You divide by the mass, then it turns out, oh, look at this. The mass sort of drops out, so the acceleration is independent of the mass of the object, right? But also, this is kind of indirect, right? It's very indirect kind of a demonstration, right, through Newtonian physics, right? That mass is indeed irrelevant as far as acceleration, and therefore speed goes. Whereas this argument is much more directly, right? So you would almost suspect that, right? And because this is such a logical argument, right? You would expect this to be, again, much more foundational, much more fundamental to something like physics.